All right, hi everybody. Sorry that this video is a little bit late in coming out. We didn't get back till pretty late last night, and then a lot of stuff going on today. So this is the first chance I've had to kind of sit down and finish out our discussion of direct products. We started this discussion on Wednesday of last week, and we want to take a look at the conclusion of that. On Monday, we're going to talk about normal subgroups. So we'll be moving on to a new topic. So I want to finish out direct products today. I'll be adding this video to the announcement from Thursday, and so you can expect to see that in the near future. This video is probably going to go up around 5 o'clock on Saturday. So we talked about the definition of a direct product last time, and now that we know what a direct product is, we want to start viewing direct products as groups and talk about some of the elements of groups that we've been talking about all semester. In particular, the order of an element in a direct product. So I want to prove for you that the order of an element in a direct product is equal to the least common multiple of the orders of the individual elements in the groups that they came from. This is going to be important for the problems that are coming ahead. And it gives me a chance to talk about a proof technique that I haven't really touched on very much, and that is proving that two numbers are equal to each other. So here, this is a number on the left-hand side. I'll call it t. This is another number on the right-hand side. I'll call it s. So ultimately, what we're trying to do in the proof of this result is show that the number t equals the number s. And when you prove that two things are equal, for showing that, say, t equals s, the way that you do that is you show that t is less than or equal to s, and then you show that s is less than or equal to t. If a number is less than or equal to and simultaneously greater than or equal to another number, the only way that can be true is the two numbers have to be equal. So this is the outline of the proof that we're going to take. So for our proof here, let's let EI be the identity element of the group GI. So let EI and GI be the identity, and let S equal this least common multiple. And let's let T be equal to the order of the element. Then here I'm going to show that T is less than or equal to S. So we're going to show this first. Since S is a multiple of the order of the individual elements for each I, then what you know is that if you take the entire element raised to the s, we know that this is the same thing because of how operations work in a direct product. Remember, they're component-wise. So that's taking G1 to the s, G2 to the s, and so on. But since s is a multiple of the order of these things, then if I raise any of these individual elements to s, all I produce is the identity. So this is simply going to be E1, E2, up through En. But remember that T is assumed to be the order, right? T is assumed to be the order of this element. S then is a multiple of these, which means that you're producing the identity. So if you raise this element to the s, you produce the identity, but t is the smallest such value for which that can occur. So this says that t must be less than or equal to s because t is the order. Now, if I want to flip it around and show that s is less than or equal to t, the way that we're going to go about doing that is by observing that if I take each of these elements and raise it to the t, we know that that is the identity or excuse me, we know that that's the order of this element. We know that's the same thing as G1, G2, all of that raised to the T, which is the same thing as the identity. But in this case, this says T is a multiple of the order for each I. We know that it's the order of this element, but individually for each of these, since G1 to the T is E1, we know that T is a multiple of whatever the order for this element is. And the same thing is true across the board. But S is assumed to be the least common multiple, but S is the least common multiple. So that implies that S is less than or equal to T. So you can't have both T less than or equal to S and S less than or equal to T without S being equal to T. So the conclusion here is that S is equal to T. So we have this result that you can find the order of an element in a direct product by taking the least common multiple of the orders of the individual elements in the direct product. So we're going to be doing a lot of least common multiples coming up very soon. All right, let's take a look at how we would use this. So I want to find the number of elements of order 7 in Z49 plus or across Z7. So if the order of the element AB is 7, then based on what we just did, that implies that the least common multiple of the order of A and the order of B is 7. So I'm just gonna kind of do a little case-by-case thing. Case 1, we need least common multiples of 7. Well, remember that the orders of the individual elements in these groups has to divide the order of the group by Lagrange's theorem. So Z49 is a group of order 49, which means the elements either have order 1, 7, or 49, right? So I know all the elements in here. So if A is an element of Z49, then I know that the order of A is 1, 7, or 49. Similarly, when you look at Z7, if I have B as an element of Z7, then I know that the order of B is either 1 or 7. So what we're looking for here are combinations of elements whose order would be 7. So combinations of elements whose order would be 7. So the first case is you've got element A with order 7, you've got an element B with order 7. Both of them have order 7. So the easiest way to do this is to use the phi function. We'll talk about that on the next example, but I just kind of want to list them out so that we understand where this is coming from. All of the elements that have order 7, so A would be an element of this set. These are the elements that have order 7 in Z49. They're all the multiples of 7. B, as its choice, would be 1, 2, 3, 4, 5, and 6. There are an equal number of elements, and remember this is because phi of 7 is equal to 6. Remember the phi function of the order tells you how many elements of that order exist in the group. So there's 6 elements of order 7 in both groups. So you've got 6 choices for A, you've got 6 choices for B. So if you think about AB, you have 36 choices. And that's just case 1. Now, if you move on to case 2, in case 2, the order of A is 7, and let's say the order of B is 1. If you do the phi thing again, you know that phi of 7 is 6 and phi of 1 is 1. So that means there are 6 times 1 equals 6 total choices. And then finally, for case 3, if the order of A is 1 and the order of B is 7, well, this is identical to the case. This is identical to case 2 directly above, just switched. So this would also be 6 total choices. So if we're looking to create an element of order 12, case 1 says we've got 36 ways added to 6, added to 6. So there would be a total of 36 plus 6 plus 6, or 48 elements of order 7. So when you look at this potential, this problem, there are 48 elements of order 7 in this group. And this group would have 49 times 7 total elements. So what is that? 280, 63, 343. So there'd be 343 elements in this group, and 48 of them have order 7. Now, clearly, we don't want to brute force this by listing out every single element and figuring out which ones have order 7, which is the reason we're talking about this in the first place. Ways of doing this without listing out all of the elements. Let's take a look at another very similar problem. This one will be slightly more complicated. But I just want to remind you of the big thing here. If you look at what that we're using, which is the theorem from section 4. So if you go to theorem 4.4 in the text, it says that if D divides N, where N is the order of the group G, then the number of elements of order D in G is given to you by the Euler phi function of the divisor. So this is the really big result from section 4 that we're going to be using in this section. So if you need to go back and review the uses of that theorem, I would recommend you do so. But that's the big thing that we're using here. So for this particular problem, I want to find the number of cyclic subgroups, not elements. I want to find the number of cyclic subgroups. So let's talk through this. I know that if I'm going to have a cyclic subgroup of order 14, I have to have a generator of order 14. So I'm going to look for elements A, B with order 14 in Z196 cross Z49, because I know that those are potential generators. And we'll talk about what that's going to imply in terms of our working of this problem. So we're going to look for potential generators here. So let's see, case 1, because I know that whatever this element AB is going to be, it having order 14 is the same thing as saying the least common multiple of the order of A and the order of B is 14 by the previous result. So I'm looking for possible combinations of elements in Z196 and Z49 whose least common multiple is 14 in terms of their orders. So we could list all the divisors of 196 and all the divisors of 49, but because the number is so low, 14, there's only so many ways that you can have a least common multiple of 14. So case 1 here is, let's let the element A be 14. Let's let the element B be 7. Or let's let it be 1. I'm going to lump both of those into this case. So both of these, if you have an element of 14 from the first group, by the way, 14 does divide 196. You should check that. Don't just assume that there's a subgroup of order 14 and 196. Remember, the converse of Lagrange's theorem is not true. So just because 14 divides 196 does not mean that this subgroup has a group of, does not mean that this group has a subgroup of order 14. So we're looking at the least common multiple of elements A and B in this case, and that would be 14. So let's think about it. So the element A that has order 14, we know that there are phi of 14 of those. Phi of 14 is 6. That's the number of integers that are less than 14 and relatively prime to 14. There are 6 of those. We know that phi of 7 is going to be 6 also. And we know that phi of 1 is going to be 1. So this OR thing is kind of interesting because I want to make sure you put this together correctly. If you're counting this, this would be that there are 6 times 6 plus 1, or 6 times 7 equals 42 choices. So there are 42 ways for that case to occur. Remember, you can think of, we need A to be 14 and we need B to be this, or and is multiply, and or is add. So if you kind of want to think about the wording that I'm using here. Case 2 is that the order of A could potentially be 2, and the order of B could potentially be 7. Okay, and you might think, well, why not? Why can't I reverse these? Why can't I say the order of A is 7 and the order of B is 2? I can't do that because 2 doesn't divide 49. So that's not a possible case for us. I have to have something which divides the order of the group in order for there to be a subgroup. So for this potential case, what we have is just a similar layout here. Phi of 2 is 1. Phi of 7 is 6. And so there are 1 times 6 equals 6 total choices for this case. So we've exhausted the cases, but we haven't answered the question, because when you combine this case and this case, you know that those two things combined say that there are 48 total elements of order 14, which means there are 48 generators. But remember, each one of these generators is going to create a group, is going to create a subgroup having order 14. We know that there are 6 elements of order 14 that will get generated there per group. So there are actually, in terms of the total number of subgroups, there are actually 48 generators, but each generator is going to is going to have each generator is only going to generate a subgroup containing 6 elements. So the 48 generators, there's really only 6 congruence classes of those, because phi of 14 is 6, right? So an element of order 14, there are 6 of those, which means that when you combine these things, that 48 generators divided by the 6 possible generators, if you will, up to some order, 48 divided by 6 would then give you 8 distinct cyclic subgroups. And so what's going on here is, just because you have an element A, let's say, that has order 14, right? You can list, and you would have A, you would have A squared, you would have A cubed, you would have A to the 4th, you'd have A to the 5th, you'd have A to the 6th, and so on, right? And if the element A has order 14, then eventually this will conclude with A to the 13, because when you get to A to the 14, you will get E. So that is going to be your 14 elements. The problem with that is, since we know that the group itself has only 6 elements of order 14, right? Then each one of these, you divide it by 6 to get the distinct ones, because there's going to be some overlaps between the cyclic subgroups that are generated by these 48 different elements of order 14. All right, let's take a look at another similar example. And that is, when can we expect a direct product to be cyclic. So when do we know a direct product of groups is cyclic? Okay, it turns out that in order for a direct product to be cyclic, you have to have the orders of the groups involved being relatively prime. Because if they aren't relatively prime, like in the previous example, then you're going to have some overlaps where there are non-distinct versions, and that'll keep any one element from generating the whole group. So the idea is if you have a direct product of several groups, it's going to be cyclic if and only if all of the group orders are relatively prime. Let's actually kind of prove that. I'm going to do it in the case for two groups, but you can use induction to show it for the general case. So let's let the order of G be the number M, and let's let the order of H be the number N. Then we can say that the order of the direct product of G and H is M times N. Now, this is an if and only if statement. So remember, if it's an if and only if statement, I have to prove the forward direction and I have to prove the reverse direction. So I'm going to suppose that the GCD of M and N is equal to D. And I'm going to look at a generator because I know I'm assuming it's cyclic. So I'm going to suppose that the group G cross H, or the direct product of G and H, is generated by the element GH. But since you can say that the element GH raised to the MN divided by D, remember D is the greatest common divisor of M and N, so D would divide M times N. You can say that this is the same thing as G to the MN divided by D and H to the MN divided by D. That's just by definition of how operations work. But then you can say, well, this is G to the M to the N divided by D. N divided by D is an integer power because D is a divisor of N by definition here. And you can have H to the N of M divided by D. And what you're getting from that is we assumed that the order of H is N and the order of G is M, and G and H are finite cyclic groups. So the order of G is what's generating the group G, so G would have order M. So G to the M is E, and H to the N, right here, H to the N, since the cyclic subgroup generated by H, capital H here is N, E, H to the N would also be E. So that tells me that MN divided by D is equal to EE. So what this says is that MN, which is the order of the direct product, has to be less than or equal to this power here. So MN has to be less than or equal to MN divided by D. Because remember, the order is the smallest, the order of the group is the smallest power that gives you EE as a result. So MN has to be less than or equal to MN divided by D. The only way that's true is if D is equal to 1. But remember, D is the GCD of M and N, so that would have to be 1. So this says that M and N would have to be relatively prime. So if we assume that the group is cyclic, we can show that M and N, the orders of the two groups, have to be relatively prime. So if we want to walk it back the other direction, we want to say, okay, let's let the G be generated by element G. Let's let H be generated by element H. And let's suppose, because we're doing the reverse direction, let's suppose that M and N, the powers here, are relatively prime. We want to show that this implies that the direct product is cyclic. But if you look at the order of GH in this case, by definition, since it's an element of a direct product, it's the least common multiple of the orders of the individual elements themselves. And the least common multiple of m and n, since m and n are assumed to be relatively prime, is m times n. But that's equal to the order of the group external product. So GH generates the direct product, which means that the direct product is cyclic. So in either direction, we've proven the result. The main takeaway here is you will only get cyclic direct products if your cyclic groups that build them have relatively prime orders. So this is going to mean that we can only decompose direct products in certain ways and maintain the cyclicness. One way that I want you to think about this is, this is sort of a direct corollary of this previous result. If I have a integer mod m or integer mod n, whatever the case may be, and I know its factorization, right? Then I can decompose it this way, but only if ni and nj are relatively prime. So I can only decompose this thing isomorphically into a direct product, assuming that I'm splitting things across relatively prime factors. So I want to just kind of show this off because it's going to be really important to us going forward. How would I rewrite this direct product in as many equivalent forms as possible? And then I want to ask you the question, is this isomorphic to Z140? You'll note that you've got 2 times 2 is 4, times 5 is 20, times 7 is 140. So I'm going to eventually get around to asking, is this direct product isomorphic to Z140? So a couple of things here. Each of these individual groups, because they are the additive group of the integers, each one of these is cyclic. So each one of these is cyclic. All right, so each one of these is cyclic. Z2, Z2, Z5, Z7, all of these are cyclic because they're the integers modulo n. Is the direct product of these guys cyclic? And then we're going to look at different ways to rewrite it. So let's just kind of break it down step by step. So if I looked at Z2, product Z2, product Z5, product Z7, remember I can only combine if the orders of the groups are relatively prime, okay? So this would be isomorphic to, let's start off by combining 2 and 5 are relatively prime. So Z2, 2 and 5 would give Z10 and Z7. So I know that that pairing is isomorphic. So I'm just using this result where I paired Z2 and Z5. So 2 and 5, 2 times 5 is 10. So that gives me Z10. I can also then combine 10 and 7 because I know that 10 and 7 are also relatively prime. So this is going to be isomorphic to Z2 direct product Z70. And that's as far as I can go there. But what if I had decided to do something different? So what if instead I took the Z10 and I basically did I read this from left to right instead of from right to left, and I said, okay, Z10 is isomorphic to, well, its factors are 2 and 5, but I wrote them in a different order. So Z10 I wrote as, so right here, Z10 would be Z5 and Z2. Notice that all that did was let me switch the order that I had here originally, but that is a different group. Right? This is a different group. If you switch the order in a direct product, it is a different group. So I could switch the orders of the elements here. Then Z2 and Z7 are next to each other. Those are relatively prime. So I could do Z2 plus Z5 plus, let's say, Z14. That's fine. 14 and 5 are relatively prime, but that would give me what I had right here. So I'm not going to write it down any different, but 2 and 5 are relatively prime. So this would give me Z10 direct product Z14. And you just keep doing this, right? So you could see here, if I had gone from the line before, so if I take the line directly before this one, Z2 and Z5, I could write this as Z10 here, plus Z2 plus Z7. Right, and there's really no end to this because I can switch orders. I know that this is Z10, Z7, Z2, which would be Z70, Z2, right? Which I could write as Z7, Z10, and Z2. But here's the thing, I keep kind of running into a barrier here because I want to take one more step and combine all of them, but I can't do that no matter how much I want to, because, you know, when I get down to 2 of them, I got down to 2 of them here, and I decomposed it down to 2 products here. And in both cases, what you see is 2 is not relatively prime to 70, so I can't combine these. 10 is not relatively prime to 14, so I can't combine these. So my point is that this thing right here is not isomorphic to Z140, and that's because Z140 had a repeated factor. Anytime the order of the group has a repeated factor, like 2 is a repeated factor of this prime group, of its prime factorization, I know that I can't fully decompose it into its prime factors like this. So Z140 would not have this direct product representation. No matter what I do, I can't write Z140 that way. So this group is cyclic, but that must mean that this group is not. So this direct product is not cyclic, otherwise they would be isomorphic. This direct product is not cyclic, even though each of its member groups that compose it is cyclic. So the question we ask now is it possible to do this with other groups? One of the groups that we've studied in this course a lot are the U groups, the group of integers that are relatively prime, like U10 would be the groups of integers that are less than 10 that are relatively prime to 10 under multiplication mod 10. The answer is yes, we can do this exact sort of decomposition with the U groups, and it turns out to be very useful. But in order to do that, I need to define a new group that's based off of these U groups. So this new group that we want to define is U sub k of n. And that is for each divisor of n, U sub k of n is the set of all x in n that is relatively prime to k. So if you're in UKN, first you're relatively prime to n, then you're also relatively prime to k. So let's do this. For example, I'm looking at U21 here. So let me write out the elements of U21 real quick. They are 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, and 20. And we're looking out of that list for all of the elements in this list that are also relatively prime to 3. So if you're looking for the elements that are relatively prime, or excuse me, not relatively prime, I keep saying that. You're relatively prime to n, but you're equivalent to k mod, you're equivalent mod k to 1. So you're 1 more than a multiple of k, right? So all the elements that are 1 more than a multiple of 3, right? So look, all the elements that are 1 more than a multiple of 3, well, you would have 1, you would have 4, you would have 10, 16, 19. Those are all the elements that are 1 more than a multiple of 3 out of U21. So now we're looking for all the elements that are 1 more than a multiple of 7. So they're equivalent to 1 mod 7. So all the elements that are equivalent to 1 mod 7, 1 more than a multiple of 7. That would be 1, because the identity is always going to be in there. And that would also be 8. So there are only 2 elements of this this new set that we're forming. And it turns out that this new set that we're forming, this new U group, U sub k, is always going to be a subgroup of the original U group. So this is a way that you can hunt for subgroups, is take all the divisors of the order of the U group and form these U sub k groups. So I actually want to prove that this is a subgroup. The proof is not particularly difficult. We're going to use the finite, since all of these U groups are finite subgroups, or finite groups, we're going to use the finite subgroup test. So let's let A and B be in U sub k of n. Then that implies that A mod k is equal to 1. And B mod k is also equal to 1 by definition. Thus, if you look at the product AB mod k, since both of those are equal to 1, then AB mod k, which we know is A mod k, B mod k by definition, this is also equal to 1. But this implies that AB is an element of UK of n. So UK, the U group sub k, is closed under multiplication mod k. And I should mention here, UK is a subgroup of UN. The operation here is under, it's no longer under multiplication mod n, it's under multiplication mod k. So it doesn't inherit the mod n operation of UN, it inherits the mod k operation because you're looking at things mod k equivalents in this group. So UK of n is closed under multiplication mod k. And since 1 has to always be in these sub k groups because you're equivalent to 1 mod k, then U sub k of n is non-empty. So if you have closure and you're non-empty, then that implies that UK is a subgroup of UN by the finite subgroup test. So I know that this new subgroup structure that we're introducing here on the U groups, I know that they will be a subgroup. Okay, so this gives us enough ammunition now that we can write UNs as external direct products, just like we can write Z mod n. And it's going to be a very similar approach. So the way that we do it is if you have a factorization of the M for UM, and you know that the elements in the factorization are relatively prime, just like for the Z mod M groups, then we're going to be able to decompose them in the same way. We can also decompose them in terms of the UK groups, because it turns out that US ST is isomorphic to UT and UT ST is isomorphic to US. So if you have a product ST inside here, you can write it you can decompose it as a product of the two U groups separately, but then you can also write them as these U sub k groups. So what I'm going to do here is I'm going to show you an example of this. I'm going to take the group U315 and I'm going to write it in as many equivalent forms as possible. So if I take U315, I first want to come up with a factorization of that group into relatively prime factors. So not a prime factorization. I'll show you the difference. So 315 is 5 times 7 times 9. And the reason I don't decompose 9 into 3 times 3 is because 3 and 3 would not be relatively prime. So for the purposes of doing this decomposition, 9 is as far as I'm going to take that. Remember, that's a repeated prime factor there. So these repeated prime factors we can't decompose, but all the other prime factors we can decompose. So this is going to be, this is going to imply that U of 315 is isomorphic to the direct product of U5 and U63. So all I did there was take I did the first one and then I combined the second two. But I could have taken the middle one and combined the other two, or I could have taken the last one and combined the first two. And, you know, of course, I could have just split all three to begin with into U5, U7, and U9. So all of these orders, 5, 63, these are all relatively prime because they don't, you can tell they don't share any prime factors when you have it written in this form. So this is what we call a relatively prime decomposition, as opposed to a prime factor decomposition. It's slightly different. And with these UK groups, we know by definition here that U9 is going to be isomorphic to, well, the way that this works is if you take one of the prime factors, you can write it as isomorphic to the product, but with the missing factors mod S in this case. So in other words, if I just want to talk about what U9 is isomorphic to, the missing factors are 35. So this would be isomorphic to U35 of the original 315 group. You can also say, for instance, that U35, its missing factor would be 9, so it's isomorphic to U9 of the original group. You could say U5, then the missing factor for 5 would be 7 and 9, so this would be 63. It's isomorphic to U63 of 315. And U63 would be isomorphic to U5 of 315. And then finally, if we looked at, say, U7, 5 times 9 would be 45. So this is isomorphic to U45 of 315. And U45 would be isomorphic to U7 of 315. And so what I could do is I could take all of these decompositions that I have here and replace them with the UK groups instead. So U5, I could write this as U63, 315. In other words, it's like I'm decomposing U315 into all of the different congruence classes modulo its products in its relatively prime decomposition. This is going to play a big role. I haven't shown you why we're doing this yet, but this is going to play a big role down the line in terms of one of the major results of the course, because we're going to use this like we do prime factorizations of integers, like since grade 5. We're going to use this structure that we're developing here to do kind of like prime factorizations of groups, which is one of our ultimate goals here. So to do this more reliably, to come up with better, a better working base, one might ask the question, is it possible that I can go even further with this? In other words, is it possible that I can take these U groups, which I can decompose into smaller U groups, and then further decompose those into these integer mod N groups, which behave very similarly in terms of their decompositions? And the answer is yes. And this is a really important theorem that's not laid out as a theorem very well in the textbook. And so I'm going to refer to it as Gauss's theorem. So Gauss's theorem says for these individual U groups, how can we equate them isomorphically to the integers mod N? So it turns out that U2 is isomorphic to the identity element, just 0, the trivial group. If you wanted to call it Z sub 0, I guess you could, but U2 is isomorphic to Z sub 0 or 0. U4 is isomorphic to Z2, and that one's easy to prove. Just write out the elements of U4. You can show that there's a one-to-one onto operation preserving map between those two. It's pretty easy to show that. If you have a power of 2, because remember what causes this issue are the repeated factors, right? So if you have a repeated factor of 2, then you can isomorphically decompose it this way. You can decompose it into 2 to the 1 and then 2 to the n minus 1. So if it was, so for example, if you had U to the 16, we know that's the same as U to the 2 to the 4, which according to Gauss's theorem would be the same as U2 direct product U, let's see, this would be 2, you just go one less, right? So this would be 2 cubed, right? So it's still adding up to, it's still adding up to 2 to the 4th, but it's 2 cubed, right? So 2 cubed would be 2, in this case, 2 to the 4 minus 1, or 2 cubed. And this is for n greater than or equal to 3. So this only kicks in once you get to like talking about U8 and above. So powers of 2 behave pretty predictably. In fact, you could just keep this going, right? So this would be U2. U2 cubed I could use as well this way, right? So U2 cubed would be, oh, sorry, I write U, it needs to be Z. So this would be Z2 and then Z2 cubed. And that's as far as we could take it. So this is isomorphic to Z2 direct product Z8. So typically we don't write it that way. Let me change it like that. So this would be applying Gauss's theorem to U16. You could rewrite U16 as Z2 direct product Z8, but you couldn't decompose it anymore because all of the prime factors of Z8 are relatively prime to each other. So you wouldn't be able to decompose this any further. And then finally, if you have any other repeated prime factor, then you can decompose it to the difference between p to the n and p to the n minus 1 for p being an odd prime. Okay? So with these results, we can write any U group as an external direct product of cyclic groups, meaning that we can show that any U group has some factorization in terms of cyclic groups. It turns out that cyclic groups are the prime factor building blocks of all groups, and that's why we're really focused on those. We're eventually going to show that every abelian group can be written this way. So it's only really the non-abelian groups that are not well behaved. Abelian groups, we understand their structure very well. And that's one of the end goals of the first semester of this course, is to completely understand the structure of any finite abelian group. All right, so let's practice this, decomposing these real quick using Gauss's theorem. So we'll start with U385. It is isomorphic to U5 times 7 times 11. So that's its relatively prime factorization, which is actually its prime factorization in this case. We know that that's isomorphic to U5, direct product U7, direct product U11. But using Gauss's theorem, I can write U5. If you have a prime factor right here, U to the P for any prime factor would be isomorphic to Z P minus 1. You can see there, because if n is 1, you have U to the P is Z to the P to the 1 minus P to the 0. P to the 0 is 1, so you get 1 less than the value there. So when I'm looking at U5, that would be isomorphic to Z4. When I'm looking at U7, that would be isomorphic to Z6, and U11 would be isomorphic to Z10. And because 4, 6, and 10 all have relatively prime factors, I can't really decompose that any further. I suppose I could do the following, though. I could say, well, this is Z4, Z6 is Z2, Z3, and Z10 I can write as Z2, Z5, but that's really about as far as I could take it, other than switching around orders of elements. I can't do anything with Z4 because its only prime factors are 2 repeated, so I can't decompose it any further. Finally, something like U2800, right? So this is a huge group, and I'm going to show you the importance of what it is we're talking about. This is an enormous group. I wouldn't even know where to start to look at elements of particular orders in this group, but the decomposition tells us a lot. So U2800 is isomorphic to its prime, its relatively prime factorization would be 16 times 17 times 25. You can check out the prime factorization here would be 2 to the 4th, 17 is a prime factor, and 5 squared. But these repeated factors, I just write them down without writing their exponents because it doesn't help us, right? Because they're not relatively prime to each other. So this would be isomorphic to u to the 17. And I'm going to write u to the 16 as u to the 2 to the 4. And I'm going to write u25 as u5 squared, so that we're forced to use or think about Gauss's result. So let me remind you here, Gauss's result is 2 is z2 with the 1 less power, z2 with 1 less power than the original. And u to prime power is z to that power minus 1 less, right? So this would be u17 would just be z hold on a second. I think I might have this off a little bit. So 140, 135. I think, yeah, I think, actually I was following my notes and I think I just saw a little mistake. This isn't 17, I believe it's just 7, right? So if you look, you've got 70, 42, 112. Yeah, I think that's correct. So 16 times 7 times 25 is the factorization there. So this would be U7, and U7 would be Z6. So we've got Z6 cross U to the 2 to the 4 would be Z to the 2, Z to the 2 cubed, right, according to Gauss's theorem. And then U5 would be Z to the 5 squared minus 5 to the 1. So 5 squared is 25 minus 5 is 20. So we would have Z6 plus Z2, direct product Z8, direct product Z20. So now I've completely deconstructed U2800 into these 4 direct product of 4 cyclic groups that hopefully we understand pretty well. The finale to all this is to talk about why this is important. So once we have this decomposition in place, right? Once we have this decomposition in place, how do we use it? So suppose I asked you, what are the possible orders of elements in U2800? Okay, well, remember, possible orders are the least common multiples of the orders of these elements. So if I was to list for you, so as an answer to question 1, if I was to list for you all these groups, so we'll start with Z20, then we'll write down Z2, we'll write down Z8, we'll write down Z6, and I'm just going to list possible orders, right? You have possible orders for each of the divisors of the sides of the group. So possible orders here for Z20 would be 1, 2, 4, 5, 10, and 20. Those are all the numbers that divide 20. Possible divisors of Z2 would be 1 and 2. Of 8, it would be 1, 2, 4, and 8. And of Z6, it would be 1, 2, 3, and 6. Now, think about all possible least common multiples of the orders of the elements that are coming from each of these. So, you know, if I let A be an element, so if I let A be an element of Z20, and I let B be an element of Z2, and I let C be an element of Z8, and I let D be an element of Z6, then I'm looking at all possible orders of those elements, right? So it's basically, I'm playing a big matching game here. I'm thinking, okay, 1, 2, 8, 2. What's that least common multiple? 4, 2, 4, 2. What's that least common multiple? Well, it turns out that if you list them all out for this group, which is something a computer could sort through incredibly fast, right? I'm not necessarily talking about us doing the analysis here at this point, because this is a very large group, but you know, from a computer's point of view, this would be a very easy algorithm to create, which would be just taking all the possible least common multiple combinations of these elements in these columns or arrays. And so you would have 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 30, 40, 60, and 120. This means that every element of U2800 must have one of the above orders. And that's a phenomenal result because you've got 2,800 elements in this group. 2,800 different elements, or excuse me, not 2,800, it would be whatever phi of 2,800 is, which is a large number. You have a lot of elements in this group, but these are the only possible orders that this group has. That's a big result. And so, you know, the next question you might ask is, well, how many elements are there of order 12 in this group? Okay, well, I know that based on the different choices I have here, I can use the phi function to tell me how many elements of a certain order we have for each of these, right? So I could come in here and say, you know, right alongside each one of these and put a little phi list, right? So I could say phi of 1 is 1, phi of 2 is 1, phi of 4 is, what is that, 2? Phi of 5 is 4, phi of 10 would be, let's see, you've got 1, 3, 7, and 9. So you've got 4. And then phi of 20 would be, let me just quickly, so it would be what, 1, 3, 7, 9, 11, 13, 17, and 19. So it would be 8. And then phi of 1 here would be 1, phi of 2 would be 1, phi of 1 would be 1, phi of 2 would be 1, phi of 4 would be 2, phi of 8, so 8 would be 1, 3, 5, 7, so that's 4. Phi of 1 would be 1, phi of 2 would be 1, phi of 3 would be 2, and phi of 6 would be, let's see, you would have 1 and 5, so that would also be 2. The point is, I know that this is how many elements of order 20. There are 8 elements of order 20 in Z20. I know there are 2 elements of order 4 in Z8. So if I wanted to ask a question like number 2, how many elements of order 12 are there in U2800? Well, I'm basically saying 12 is one of the possible least common multiples, so it is a possible order. What are all the different ways in which I can get orders of 12? Well, you know, you could have, you know, if we were to think through the list, you could have, you know, B is 1, D is 3, and A is 4, and C is 4. I went through the possible combinations in the notes. So if you want to reference the notes, I walk through all of this, but it literally comes down to this. There are 96 elements of order 12. By counting cases, right? You can count all the different cases that lead to having a least common multiple of 12, and then you know how many elements generate the, you know how many elements of that order there are, and by the previous examples we've done, we can count each of those cases. So the hardest part here is figuring out what the cases are that lead to a least common multiple of 12, but once you've written down all those cases, you just simply count the phi functions for each of the representatives, and you have the total number of elements. And then finally, I kind of want to make you recall a pretty obscure result from chapter 6 or section 6. It says the group of automorphisms on Zn is isomorphic to the U groups. So if there are 96 elements of order 12 in U2800, then that result says that there are also 96 isomorphisms of order 12 that map an element from Z2800 into Z2800. So this understanding the U groups also gives me some ideas of possible mappings from cyclic groups into itself. And that turns out to be really important later on as well. So what we're trying to do here is build up an understanding of how to count different orders in cyclic groups, because these cyclic groups are going to be the backbone of our building blocks for sort of like prime factorizations of groups down the line. All right, this is probably one of these topics that you really need to kind of work some of the problems that are on the skills quiz, think about some of the problems that are on the proofwriting assignment to get a good handle on it. But you really do need to get a good handle on it, because this could be important going forward, that we're able to make arguments like this. All right, I'll see y'all in class on Monday. I hope you have a great weekend. Sorry that the video came out a little bit late. All right, talk to you later.